in this video we're going to cover chapter 10, which relates to chemical bonding and Lewis structures. So first, to orient ourselves, we want to understand that elements form compounds because they want to reach more stability. And with their electrons, that means they want to reach a noble gas electron configuration, just like we talked about in chapter 9, which is the same thing as 8 valence electrons or an s2p6 electron configuration. So these statements are all true. Now, there are some elements that do not like to form what we call octet rule or have 8 valence electrons, but we'll talk about those. So there's different types of bonds. We've mentioned these in the past. Metals to nonmetals are ionic bonds. Nonmetals and nonmetals like to form covalent bonds. And also metals to metals, we like to call them metallic bonds. And basically, if you have a copper wire or a piece of iron, the electrons are pooled together throughout the atoms in that sample. So based on the periodic table, we can determine the number of electrons in an element, so based on their group. So 1A has 1 valence electron, up to 8A, which has 8 valence electrons, or a full shell. So since the noble gases are non-reactive and they're pretty stable. So the octet rule is that 8 electrons around most atoms that partake in bonds. The electrons that partake in bonds are otherwise known as the valence electrons. So the outermost shell should have 8 electrons total. That's when the valence shell is happy, and that's when the atom is happy. There are several elements that violate this rule, which we'll get to that in a minute. So for the Lewis structure, we can predict the arrangement of these electrons, how they're going to form bonds, and also their 3-dimensional or 2-dimensional structure. So we can determine both from the Lewis structure. In chapter 11, we'll go over more of the 3-dimensional structure, but in chapter 10, we talk about the 2-dimensional structure with how the Lewis bonding works. So, for example, if we have lithium, which is a positive 1 charge, when it becomes an ion, it originally has 1 valence electron. So we denote this by Li, the symbol, with 1 dot next to it. Fluorine, on the other hand, has 7 valence electrons, so it will have 7 dots, 2 on each side and 1 on the odd side. So when it becomes an ion, it will gain 1 electron. So it will become fluorine with 8 electrons. When lithium becomes an ion, it will lose an electron. So it will become Li plus 1. So in an ionic bond, there is no directionality to the bonding itself, meaning there is no orientation or specific angle at which the anion will attach to the cation. So, for example, we can just write it as, if we had lithium oxide, it would be just 2 lithiums bond to an oxygen based on the charges. So lithium is plus 1, you need 2 of them, and oxygen is minus 2. So there is no directionality to this. And the reason why is because this is an electrostatic interaction, meaning a positive and a negative combining together. So from this ionic bond, we can take it a step further, and if we had thousands of ionic bonds of one substance next to each other, these ions arrange themselves in repeating patterns called crystal lattice. Now, the crystal lattice is arranged in a way which maximizes the attractions between positive and negative ions to reach energetic stability. So here we bring in energy to this, right? So we can determine the energy of a crystal lattice depending on the charges of the ions and also depending on the identity of the ions based on this equation, and more specifically, this equation. So E potential equals 1 over 4 pi epsilon naught, which is a constant that will be given to you, times Q2 times Q1 over R. Now, Q1 is the charge of one ion, Q2 is the charge of the second ion. So, for example, and this is the absolute values of the charges. So, for example, if you have a positive 2 and a minus 1, you have plus 2 and times 1. So that would be 2. And then divided by the radius of the ionic bond, and that could be determined from adding the radii of the anion and the cation together. So here's some examples of the energetics of ionic bond formation. So from this, we can determine the lattice energy knowing the melting point of an ionic compound, because if you have a higher melting point or more charges, so if you look at this the potential energy equation, the potential energy will increase as you increase Q1 and Q2. This means if you have a sodium chloride, such as a +1 - 1 interaction, then Q1 times Q2 will be only 1. But if you have a +3 and -3, like aluminum phosphate, this will be 3 times 3, which is 9. So the potential greatly depends on the charge of the ions involved in the bond. Also, it depends on the radius. The closer they are, meaning the smaller this R value, the larger the potential energy. And the further they are, the lower the potential energy. So it's a common theme in chemistry where bonds that are shorter are stronger, and bonds that have more charges are also stronger. So we see that trend take place here, where NAF they're both smaller molecules, or smaller atoms, and they have a higher melting point, meaning more energy is required to break them apart. Meanwhile, potassium chloride, 2 slightly larger atoms, have a lower melting point. And as you go to the right and increase the charge, you see that the charge plays more of a role, because like we said before, for NAF, it's a +1 -1. So their Q1 times Q2 is only 1. For MgO, it's 2 times 2, which is 4. So it's going to be a lot larger in the amount of energy required to break that bond. So from this, we can understand the Born-Haber cycle, which basically states that we can break down a molecule that's ionically bound into its constituent elements, and we can break down that further into how this ionic bond is formed. So if we look at it this way, where if we have the formation of some metal mixing with I'll say it's a halogen gas, right? Like a fluorine gas. So the way to break down this delta H, this enthalpy of formation, that usually before this in chapter 7, the enthalpy of formations were given to us for specific reactions. But this can actually be broken down into the following. If you have one metal that is a solid, the sublimation of that metal to a gas, the energy required to do that, plus the ionization energy, which gets it into its ionic form, plus the dissociation of the diatomic gas of the other element, if it were a gas, plus the electron affinity to form an ion in the anion state, then all those energies added together, plus the lattice energy of those actually combining together, equal the enthalpy of formation. So we come up with this equation on the bottom. Delta HF equals basically all the processes required to go from the constituent elements in their natural form to the ionic form, plus the energy required to actually combine them together into their ionic bond, equals their HF, their enthalpy of formation. So here's an example we're going to do during class, and you can pause the video and try to figure out what is the lattice energy of MgCl based on the given information. So trends in lattice energy and ion size. So the larger the ion, the weaker the attraction. So that basically goes along with the equation we just went over where it's divided by R, right? So the larger the R, the lower the E potential. So the lower the energy required to make that bond. So larger ions make smaller lattice and smaller lattice energies, and smaller ions make stronger attractions and larger lattice energies. And we can see that here where the chloride is kept constant and the cation is increasing in size, and the lattice energy decreases as we get to a larger radius. Charge plays a much more important role. So if you increase the charge, just like we saw in that equation, that it plays a huge increase in the potential energy. So for example, NAF is +1, -1. You get around -900 kilojoules per mole. But if you make it a +2, -2 with around the same radius, you triple that lattice energy. So charge plays more of a role. So now we can talk about Lewis structures. So we have two types of electrons in Lewis structures. We have bonding pairs and lone pairs. So these electrons will pair up and create bonds. So in CO2, you will have, and these bonds will form in a way where to achieve the octet rule, 4 atoms that do like the octet rule, which is most of them. So for carbon, for example, carbon likes to have 4 bonds, and it's important that you memorize the number of bonds that some of these elements like, because that'll just make it a lot easier for you. So oxygen likes 2 bonds, carbon likes 4. The only way to arrange this when oxygen has 6 electrons is for oxygen to share 2 from carbon. So each oxygen will share 2 from carbon. Remaining will be 2 lone pairs of electrons in each oxygen, and the carbon will have 4 pairs of shared electrons, or 2 double bonds. And these are directional, so meaning we can determine the molecular shape from the Lewis structure in covalent bonds. So here is what we should know. So carbon loves to have 4 bonds and will always have 4 bonds, very important. Nitrogen will most of the time have 3 bonds and 1 lone pair. That's where it's the most stable. Oxygen will have 2 bonds and 2 lone pairs. Hydrogen and halogens will have 1 bond, but the halogens will have 3 lone pairs, like you see in fluorine over here. Hydrogen will have no lone pairs. So hydrogen is an exception to the octet rule because it's so small, all the electrons just like to take up the s orbital, meaning, or the 1s orbital to be specific. So that means you can have a maximum of 2 electrons. Beryllium likes to have 2 bonds and no lone pairs. That is another exception. Boron, another exception, 3 bonds and no lone pairs. Sulfur is a weird one. So sulfur could have 2, even 4, or 6 bonds. And all of those are considered to be relatively stable. Phosphorus is similar to nitrogen, but it can also form 5 bonds. So the Lewis structures below, these show for the common elements, boron, carbon, nitrogen, oxygen, and fluorine, the Lewis configuration. So with their lone pairs as dots and their preferred bonds as lines. So here's some practice that we're going to do during class. So from the Lewis structure, and here's what Lewis structures look like. So for CO2, we can first draw the dots. So I would draw 4 dots around carbon. Then you basically connect the dots. So you know that oxygen likes to have 2 bonds, and you can connect the dot of oxygen to one of carbon. Do that twice because oxygen likes to have 2. And then you see that carbon ends up with 4 bonds, and everything is stable and happy. Another question I frequently get is, how do we know which atom goes in the middle? So there's 2 ways of doing that. 1, if you have carbon, usually it's carbon. 2, if there is less of an element, so such as NO2, it's probably going to be the one with less of the element. So it's going to be nitrogen in that case. P2H4, well, it's never hydrogen, right? Because hydrogen can only have 1 bond. So if there's another element that's not hydrogen, hydrogen is always on the end, and it's always bonding to the central atom or something different than, it's not the central atom. So if you have, here's an example, SO3, where there's 1 sulfur, therefore it's probably going to be in the middle. So that's kind of there are some small exceptions to that, but that'll work for 90% of the cases. So a formal charge represents even though we're not talking about electrostatic interactions, with covalent bonding and Lewis structures, we can actually have a charge. This is called the formal charge. So a stable molecule will have a net 0 formal charge. So atoms do not like to have a high formal charge. Now, there is a formula for formal charge, which is the valence electrons minus the non-bonding electrons minus 1/2 the bonding electrons. All right, now you can take that and memorize that, and you can probably get by with it. But an easy way to know it is if you just look at an atom bound in the Lewis structure. We'll look at this oxygen on the left in CO2. All you have to do is take the valence number, so oxygen is 6, and you subtract each individual dot and lines. That's all you do. So you do 6 minus 1, 2, 3, 4 dots and 2 lines. And you come up with 0. Carbon, the valence number is 4. Subtract all the dots, there are no dots. Subtract the lines. So that's 4 minus 4, 0. In this case for selenium, selenium is just like oxygen, where it's 6. So 6 minus the dots, 2 dots, makes it 4, minus 3 lines. So plus 1. Selenium is plus 1. The oxygen on the top, you have 6 minus 6 dots minus 1 line. So minus 1. Very easy to do. So that's basically how you figure out formal charge. Now the idea is to minimize the formal charge. So even if there's a net formal charge of 0 on a molecule, if the 0 is comprised of a plus 2 and a minus 2, that is less stable than having all zeros all around, or even a plus 1 and a minus 1. So when arranging these Lewis structures, there are going to be more complicated examples that you need to work around a little bit and minimize these formal charges. And it's never good to have a formal charge on the central atom. That's usually undesirable. This is why SO3 2- prefers to have -1s on the oxygen rather than have a formal charge in the middle, rather than having a large formal charge in the middle. So we can have resonance structures. Now this plays a big role in organic chemistry, but basically we can say that in a molecule that has three identical bonds, or three identical arrangements, where like SO3, you can have a double bond in between either of the oxygens. Now, these structures are considered identical, and these bonds can actually shift to different oxygens, and we can actually come up with a resonance hybrid. So it can be represented by all three of these arrangements, and they're virtually identical. Now, in these covalent bonds, unless you have the same atom bound, the same element bound like H2 or O2, or elements of similar electronegativity, we end up with unequal sharing of the electrons between them. So certain elements like to pull electrons in a covalent bond more than others. This is called electronegativity, and it results in a polar covalent bond. So electronegativity is the measure of pull of an atom that has to bonding electrons, and it's similar to ionization energy. So it increases across a period from left to right and decreases going down. So fluorine is the most electronegative element, meaning it has 7 valence electrons. It really wants to get that 8th one, so it will pull that electron in a covalent bond a lot. Francium is on the bottom left, and it's the least electronegative atom. The larger the difference in electronegativity, the more polar the bond. So here's the numbers for electronegativity that we do not need to memorize, but they will be given, and you will be expected to subtract them from each other to figure out if the bond is polar or not polar. So the rule is, let me see if the rule is here. Here's the rule. So the rule is, if the electronegativity difference is 0, we have a pure covalent bond, meaning there's a exact equal sharing of the electrons in the bond. If you have a difference of 0.1 to 0.4, you have a non-polar covalent. So pure covalent and non-polar covalent, there is little pull in the electrons in the bond. If you have 0.5 to 1.9, the bond is considered polar covalent, and any difference larger than 2, the bond is considered ionic. I wouldn't even focus on the last bullet point because you know it's ionic if it's a metal and a non-metal. So here's the scale. Let's say if we have, there are some weird examples. Let's say you have hydrogen and phosphorus, right? They're both 2.1. So that bond is considered nonpolar. But in a molecule, you might have an asymmetry between those nonpolar bonds, making them polar. So it depends. But we'll talk about that more in chapter 11 when we go over shape. So here's an example of hydrofluoric acid. There is a huge electronegativity difference of 1.9, and it is a polar covalent bond. This is what makes it a weak acid, because if you have a larger difference in electronegativity, this creates a stronger bond. So it actually creates, it becomes more of a weak acid, because this bond is going to be stronger than an HCl bond, which breaks apart more easily and ionizes. Here is that HCl bond in the middle. So you have a difference in polarity of 0.9. So it's a little bit weaker than the HF, which makes it more of a strong acid, and the H plus can come off easier. Then we have metallic bonding. So metallic bonding, you basically have a sea of electrons that are flowing between all of the different atoms of the metal in the sample. And this is why metals are mostly conductive, because the electrons can flow freely throughout the metal. So trends in bond energies, remember we said that shorter bonds are stronger. So if we have a single, double, and a triple bond, the triple bond will be the strongest, the double bond will be second, and the single bond will be the weakest. So the shorter the bond, the stronger the bond. And this also plays a role with the size of the atom. So carbon and carbon is 837. Carbon and nitrogen triple bond is 891. So it's a little bit stronger because nitrogen is, so there's actually an electronegativity difference there, which actually pulls the electrons closer, which makes it a little bit stronger. So, and also the shorter the bond, the less the energy. The bond length plays a role, so that's basically what we just said, but they kind of go hand in hand. So if you have more bonds, so single, double versus triple, the distance will decrease and the number of bonds will increase at the same time. So basically, if there's more bonds, it's stronger and shorter. Stronger is shorter. Longer is weaker. And then we can determine from these bonds themselves, and I kind of mentioned this in chapter 7, you can find the enthalpy of reaction a different way by taking the sum of the bonds broken minus the sum of the bonds formed. And this is different than what we did, because before we did enthalpy, which was the change in enthalpy of the products minus the change in enthalpy of the reactants. But in this case, to find the enthalpy based on just the bonds, we can take the bonds broken, which is the bonds of the reactants, minus the bonds formed, which are the bonds of the product. So for this case of H2 plus O2 equals HOOH, what we can do is take bonds broken, which is HH of 436, plus an O double bond O, which according to the table is 498. Add those together, subtract 2 HO bonds, so HO is 464 times 2, plus an OO single bond, which is 142. Make that subtraction, and you will get your answer. So that's it for chapter 10. If you have any questions, please leave a comment. Please smash that like button and subscribe for more